If you ask people around about what they do in their free time, you'd expect things like reading, cooking, or maybe even playing with computers to come up quite frequently. But how often would you hear something like designing computer processors for fun? Well, that's exactly what I do, so I'd like to take you on a little walk through this niche but very interesting hobby. Pretty much all of us use some sort of a computer these days. Although they've become so user-friendly that we hardly ever think about what makes them tick. Well, this one doesn't tick, it's dead. Anyways, I want to show you all the inner workings of a CPU, but we're going to start somewhere and we're going to start small. In the simplest terms, all the CPU does is logic operations, like OR and AND. These are represented in diagrams with logic gates, each shape representing a different operation. Take a look here. This is a physical OR gate. The name says it all. If either this button or this button is pressed, the light turns on. It stays on when I press both at the same time. Here's the so-called truth table for it. This, on the other hand, is an AND gate. The light will turn on only if both this button and the other button are pressed. It's actually combining these gates which allows us to create more complex circuits, ones that can even, say, add or subtract numbers. This is exactly what an ALU is for. ALU stands for Arithmetic and Logic Unit, and it's basically the internal calculator of the processor, built from loads of these basic building blocks. The ALU alone wouldn't be very useful though. You need a way to store the results of these calculations, otherwise all you've built is a fancy underpowered calculator that certainly won't play this video or run Doom or anything. Here's where a little thing called a register comes into play. It's basically a tiny memory cell for the CPU. It remembers numbers very well, but isn't great for long-term storage. It works kind of like a whiteboard. You write stuff to it, and then you can see what's inside. Then if you need the space for something else, you can just overwrite what was there. Registers are really close to the CPU, so they're really quick to access. But there's just a small number of them, so they're not great for general storage. For that, a dedicated block of memory called RAM might be more suited. One more thing I need to mention is how these components are all connected. Of course, you want them all to be able to communicate with each other so that the ALU can, say, add the numbers stored in registers, and the registers can push and pull data in and out of RAM. This is handled by buses. Well, not literal vehicles, but that's what they're called. In our imaginary CPU, the registers may be connected to the ALU as inputs, and the ALU's output could be hooked up to the registers for storage. You can see, however, that if we just connect them all and they're constantly shouting their values at each other, that this whole thing is going to become quite chaotic after a while. Therefore, we need good old German Ordnung to keep them under control. We need a control word. Simply put, it's just a bunch of wires, and depending on which ones are powered, different components are allowed to access the bus. In principle, designing the CPU is the easy part, but a computer's just a useless, expensive brick unless there's a way to run software on it. When it comes to programming, you might be familiar with languages like Python or JavaScript or even C++ if you're fancy, but as you can probably guess, there's no way our little 70s time machine can speak those. Actually, the only thing it understands is those control lines we talked about earlier. Programming with those directly is called microcode. Here's a bit of real microcode from my latest contraption, and you can really see how bare bones this is. This command enables the control lines that tell the ALU, hey, you should add these two numbers, you know? This will literally power a line that enables a register called A, and this says that the result of the addition should also be saved in A. The rest of these also turn on different wires, but they're, let's say, out of scope today. This text form is converted to binary numbers which the CPU can read. It's as simple as, if there's a 1 here, enable this control line, and so on. The conversion is done by a microcode compiler, and as much as I love writing them and talking about them, they're really complex pieces of software, and this is not a crash course on compilers, so I'll allow myself to skip that. As you saw, microcode is a really close to the machine way of writing code, and of course, nobody does that anymore. We need something that's easier to work with, while still being powerful and allowing us to do whatever we want with the hardware. That middle ground of complexity versus power is what we call assembly. No longer do we have to think in terms of control lines, and we can focus on the overall architecture. For example, to add 3 and 5, we just say load A 3, which puts the number 3 in the A register, and add 5, which, well, adds 5 to it. That's as easy as it gets without getting too abstract. To make the CPU understand our new assembly language, we need to write a program in microcode that tells it exactly what each command does. The snippet I showed you before was actually part of that. It told the CPU what to do when it saw an add command with number afterwards. I'm greatly simplifying here for the sake of time, and of course, assembly isn't fed to the computer in this text form. There's another special compiler called an assembler that converts these commands into yet another form of binary, and you can actually see here what the add 3 and 5 example looks like. You can see the 3 and the 5 here, and the rest is the instructions: load A, add, and halt, which shuts down the CPU. Unlike microcode, assembly programming is still sort of relevant today, especially in the world of small embedded programming. All these layers upon layers of compilers, assemblers, linkers, microcode work together to steer these tiny logic gates made out of transistors. To give you the ability to play solitaire or watch YouTube or maybe even create something of your own. I think that's fascinating. And being able to build every little bit of that system myself, as niche of a dream as it is something I've been exploring for years now. I think I can truly call it my love.